We learned how we can estimate enthalpy changes using heats of formation. We can also do that using individual bond energies. So the bond energy is defined as the energy required to break 1 mole of the bond in the gas phase. So bond energies are going to always be positive because it always requires energy to break the bond. If it released energy when bonds broke, then they would just break on their own and there wouldn't be any bonds. So the more energy it takes to break the bond, the stronger the bond. I mean, this sort of thing applies to sticks as well. Compounds that have stronger bonds tend to be more stable and less reactive. So we're going to be looking at average bond energies. So it's an average of bond energies in a bunch of different compounds. And just looking at a carbon-hydrogen bond in several different compounds, we see that the actual bond energy varies. So here, the carbon that the hydrogen is bonded to has 3 hydrogens on it, 438 kilojoules. Swap those hydrogens for fluorines, now it's 446. Put bromine in there, 402. Chlorine in there, 401. And so it changes depending on what else is going on in the molecule. But we use an average of 414. A double bond, a triple bond, those are going to be stronger than single bonds, and they're going to require more energy to break. So bond energies can be looked up in a table such as this one. Like here with carbon, you have to be a little bit careful because there's a carbon-carbon single bond, a double bond, a triple bond, and similarly with nitrogen. So you want to make sure that you've got the correct elements and the correct kind of bond. And another thing I want to point out to you is a carbon-oxygen double bond. So it's 736 kilojoules per mole, but this asterisk tells us if we're looking at CO2, then it's 799. Okay, so we've got to watch out for that one. So what we're doing here is just like what we did with the heats of formation, where we take the sum of the energies for well, let me rephrase that. It's kind of like that, but just enough not that I don't want to go there. What we're thinking about, let's just talk about this, the picture. So these 2 molecules react and form these 2 molecules. And so we can look at, well, what bonds have to be broken? Well, this carbon-hydrogen bond has to be broken. And so we go up there, we have to add energy to do that. And we also have to break the chlorine-chlorine bond. So we have to put energy in to break those bonds. When new bonds are formed, energy is released. So we've got a chlorine-carbon bond that forms and a chlorine-hydrogen bond that forms. So bond breaking is endothermic. We have to put energy in. And bonds forming is exothermic. So what we're going to do is we're going to look at all the bonds that are broken and all the bonds that are formed and add up those energies, and that will give us an estimate of the enthalpy change for the reaction. We often say that energy is stored in chemical bonds, and in a sense that's true, but in a sense it's always kind of not true also. When you break a chemical bond, it requires energy. But if we have a situation where weak bonds get broken and strong bonds are formed, then energy gets released into the surroundings. And so energy-rich compounds do that. It's not the breaking of the bond that releases energy, it's the forming of chemical bonds. So energy is released when bonds are formed. Let's look at this. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? The energy to break the bonds is greater than the energy released. The energy to break the bonds is less than the energy released, or the energy to break the bonds is about the same. So the reaction we're looking at here is highly exothermic. It's releasing a lot of energy. We've got two things going on. We've got breaking bonds. We have to put energy into that. And we have bonds forming, and that releases energy. So which one has to be higher in energy? The breaking or the releasing? Mumble, mumble, mumble. The releasing. Of course, you're right. I have no idea what you said. So the energy needed to break the bonds is less than the energy released. It's a little bit like investing. You invest some money and you hope that in the end you're going to get a bigger payback than what you put in, right? That's an exothermic reaction. An endothermic reaction would be one where you put a bunch of energy in and only a little bit comes out and you're losing money, right? So that's kind of the idea here. So a potential future fuel is methanol. Write a balanced equation for the combustion of gaseous methanol and use bond energies to calculate the enthalpy of combustion of methanol in kilojoules per mole. These types of problems can be a little tedious. So, burning of a hydrocarbon. So, we've got CH3OH. And what's the other reactant if it's burning? Oxygen. And what's it going to form? CO2 and water. So when you burn a compound that contains carbon, hydrogen, and possibly oxygen, you're always going to get water and CO2. And the other reactant will be oxygen. So there's our reactants and products. We need to balance the equation. I've got one carbon and one carbon. I have 4 hydrogens here and 2 there. So I can put a 2 in front of that and get 4 hydrogens. And I've got 2 oxygens plus 1 and 2 oxygens plus 2. So I'm going to need 1 more oxygen, but they're coming in pairs. So what I'm going to do is I'm going to double everything. Now I haven't messed up my carbons or my hydrogens, but the oxygens now I have 2 plus 2 is 4, and 4 plus 4 is 8. So I've got 2 over here. I need to get 6 from that, and so if I had 3 oxygens, that would work. So that energy diagram that we looked at, they just looked at the actual bonds that broke and the bonds that were formed. And that can get a little bit tricky. It's a little more work, but conceptually much easier to think about, well, let's just take this molecule completely apart. Let's break all the bonds. And break all the bonds here. And then we're going to make all of these bonds and make all of those bonds and see what we get. In order to do that, we have to have the Lewis structures because we have to know what bonds we're dealing with. So the CH3OH is going to look like this. and oxygen looks like that. And then over here, CO2 is going to look like that. The lone pairs aren't really that important for this problem, but they are important. The kind of bonds is really important. So in one of these molecules, if I'm going to take it apart, what kind of bonds am I breaking? Well, I've got some carbon-hydrogen bonds, right? There's 1, 2, 3 of those. 1, 2, 3. So there's 3 of those. And then I have a carbon-oxygen bond right there. And then I also have an oxygen-hydrogen bond. So I've got, in one molecule, I've got 3 of these, 1 of those, and 1 of those. Okay? So if I had a mole of molecules, I'd have 1 mole of these bonds, 3 moles of those bonds, 1 mole of this one, and 1 mole of that. But how many moles do I have? I have 2. So if I have 2 moles, that means that I'm going to have 6 moles of the carbon-hydrogen bonds that get broken, 2 moles of the carbon-oxygen, and 2 moles of the oxygen-hydrogen bonds. Any questions? You see how that worked? No? You see how in one of these, we've got 3 of these kinds of bonds that break, okay? 1 of those and 1 of those. Well, that would be in 1 molecule. If I had a mole of molecules, that's like a dozen, right? But much bigger. Then I would have 3 moles of those, 1 mole and 1 mole. But here I've got 2 moles, so I'm going to multiply those by 2. Okay? 626. Our train times keep getting erased, but it's still amusing for some reason. And then the other thing that we're breaking here is an oxygen-oxygen double bond. 1 mole of oxygen has 1 mole of those bonds, but I've got 3 moles. So I'm going to have 3 moles of that, and let's just give this another color. So I'm counting up the kinds of bonds that I'm breaking. And then I'm going to go over here and count up the bonds that I'm going to be making. So in CO2, I've got 2 carbon-oxygen double bonds. Whoops. Maybe that will be, what haven't I used? Red. Right? So there's 2 of those in 1 mole, 2 moles of bonds in 1 mole, but I've got 2 moles of CO2. So this is going to be 4 moles of CO double bonds. And then over here, let's see, I haven't used green yet. I've got hydrogen-oxygen bonds, or oxygen-hydrogen. And each mole of water would have 2 moles of those bonds. But I have 4 moles of water, so I have to multiply that, and I'm going to have 8 moles of oxygen-hydrogen bonds. So now, I need to go way back here. I'm gonna write these on the board because I'm not gonna remember. So we had hydrogen-carbon bonds, 414. We had hydrogen-oxygen bonds, 464. We had carbon-oxygen bonds in CO2. Those were 799. And then I also need a carbon-oxygen single bond, 360. So 1 mole of carbon-hydrogen bonds is going to take 416 kilojoules per mole. And I'm multiplying by 6 moles. The carbon-oxygen is 360. Again, it's 2 moles of that. Oxygen, hydrogen, 464, and I missed that one. I missed the oxygen-oxygen double bond, 498. So this one's 498. So then we can figure out how much it's going to cost to break all these bonds. 6 times 414, 24, 84, plus 2 times 360, 720, 2 times 464, 928, and 3 times 498, 1494. So if we add these all up, I'm getting 5626 kilojoules. Anybody else do the math and get the same number? So that's how much I have to invest. I'm breaking bonds, I have to put that in. And then over here, these bonds are being formed. So instead of requiring energy, these are releasing energy. The carbon-oxygen double bond is going to release 799 kilojoules per mole. And there's 4 moles of that. So I'm writing that as a negative because it's releasing that energy. And the oxygen-hydrogen, 464. And there's 8 of those. 8 times negative 464, negative 3712. Add these up. Negative 6908 kilojoules. When I break all the bonds in these guys, it's going to cost 5,626 kilojoules. When these bonds form, it's going to release 6908. So we're going to add those together. 5626 plus negative 6908. negative 1282 kilojoules. Yeah. I'm adding them because we changed the sign on these guys. So, yeah. So that's the enthalpy of combustion. That would be delta H for this reaction. Any questions? There's a bunch of details in there, but the overall concept, I think, is pretty simple. We're breaking all the existing bonds. That requires us to put energy in to invest in this process. And then as these new bonds form, they release energy, and this is how much gets released. It's released from the system, so it's negative. And then we add them together, and the net result is this will release 1282 kilojoules when 2 moles of methanol is burned. Also talking about bond length. So bond length is the average length of a bond between 2 particular atoms, again, in a large number of compounds. Double bonds are shorter than single bonds. Double bonds are shorter and stronger than single bonds, and triple bonds are shorter and stronger than double bonds. Here, just looking at carbon triple bond has a length of 120, strength of 837. Single bond, the bond length is longer and the strength is less. So if you think about it, when those atoms are close together and held by more bonds, it's harder to break them apart. A triple bond pulls them in really close. Longer bonds are generally weaker, generally. This is just some average bond lengths.